think at this stage we'll just crack on, and I will briefly introduce tonight's speaker, and then allow Alison to make her presentation. If you'd been keeping an eye on the press over the turn of the year, you would have spotted perhaps that Alison was recently awarded an MBE, and I'd like to take this opportunity to pass on my congratulations to her, certainly on behalf of the Society and its members. And Alison has been with BGS for some years now. I won't go into too many of the details, but joined BGS really after completing her PhD at Edinburgh, and has really been with BGS very much involved in the, how can I put it, the transition from perhaps conventional hydrocarbon-based energy systems, petroleum systems, more into the realm of unconventional, and particularly in this case geothermal energy systems, involved in a lot of three-dimensional geological modeling of sedimentary basins, particularly of carboniferous sedimentary basins. And Alison has been very much a leader on a number of major BGS projects involving industry, expertise as well, bringing together and developing our understanding of onshore and offshore carboniferous basins in the UK, and particularly across the Midland Valley of Scotland. So more recently, Alison has diversified, I suppose we could say, into looking at the potential for geothermal energy, particularly in the west of the Midland Valley. And as the title to her talk very strongly tells us, Alison is very much involved with the Geoenergy Observatory in Glasgow. So the title of her talk tonight is Drilling into Mines for Heat, the UK Geoenergy Observatory in Glasgow. So over to you, Alison, take it away. Thank you.
Thank you very much, Graham, and thank you very much for having me tonight. So what I'd like to do this evening, let's get my slides to advance.
Actually, Alison, just while you're doing that, I'm reminded when I see the chat button light up, because this is a joint meeting with the MIS, and one of the jobs that they do, or one of the obligations on them, is to collect a list of all the participants in the meeting. Could I ask everybody who's in attendance to go to the chat button at the bottom of the screen and just send your name into, if you open the chat box, you'll see at the bottom where it says to everyone, you can say there, send it to Mark Friel. So if you scroll down the list of names, you should find Mark Friel, Mark.Friel he is, and just send to Mark that what your name is, and then Mark will be able to copy that out and get a list of participants. So sorry about that interruption, Alison, carry on please.
That's right. Okay, so what I'm going to do this evening is, first of all, I'm going to talk about why we are developing a subsurface laboratory or an underground observatory in Glasgow for mine water heat, then talk a little bit about what it is, and then I've got a bit of a section about drilling into the mine workings in Glasgow and how we tested them, hydrogeological testing, a bit about some environmental monitoring that we've been doing around the observatory, and then finally just how we see people might want to use the observatory in the future. So first of all, I'm just going to talk about why the UK government has funded a subsurface observatory in Glasgow. And on your screen you can see a number of different reports that have been produced by the UK government and the Scottish government on energy strategy and on climate change. And really there is a big shift in recent years in government policy on our energy systems to try and reduce carbon emissions from UK energy. And so this term decarbonisation of heat is a very popular term at the moment, and it's about reducing the amount of carbon dioxide created during creating our energy and our heat in particular. And in this recent document that the UK government produced just before Christmas, which was called Powering Our Net Zero Future, there was a large section in that report about clean heat technologies for buildings, so how we heat our buildings. And so, for example, there are various targets in there, like 600,000 heat pumps a year to be installed in houses by 2028. There was other things in there, and there was also an example of a mine water scheme in County Durham included within that document. But in general terms, there's relatively little on geothermal in these government policy documents and in our energy mix at the moment. So I'm just going to have a slight diversion onto geothermal energy and what is it. So this diagram here shows a cross-section through the earth. So here we have the ground surface and going down deep into the earth. So this red pinky blob here may be a granite, for example. And as we go deeper into the earth, then the geothermal gradient, the temperature increases. And we get heat coming up from the center of the earth, which is conductive up towards the surface. But we also get heat from the sun, and that heat can be conducted into groundwater, which then moves through the rock strata. So there are really two sources of heat within the ground, so from the sun and from the earth. And geothermal, in its broadest sense, kind of encompasses all of those different types of heat. But more in the industry, people talk about ground source heat, which is the more shallow, low temperature geothermal, and sort of true geothermal, which is the deep geothermal. And again, just another image here to illustrate a bit about geothermal technologies. So again, we've got a cross-section, a geological cross-section, and this cross-section shows different types of geothermal energy because there are lots of different types. So there's very shallow geothermal energy, temperatures are quite low. There's geothermal energy from mines, which is what I'm going to talk about tonight. And then there's much deeper geothermal energy where this is involving power. So the shallower technologies involve heat and ground source heat pumps. The deeper technologies involve direct heating and power from the heat of the earth. And the BGS is involved in a number of different observatories on a number of these different technologies. So the one in Glasgow, we're looking at mine workings. There's one being developed in Cheshire where they're looking deeper at the aquifers in the subsurface. And there's one in Cardiff that's looking at the very shallow geothermal. And these observatories are looking at monitoring change in the subsurface. So I wanted to just give a bit more detail about mine water geothermal. So I've got an image here, so I'll just explain what's on this image. So this is a cross-section of the geology under the ground down to about 100 meters. And it's a sequence of mined coal measures. So there are gaps in here, which are coal measures, and they're flooded with water. So since coal mining stopped, water levels have risen. So the water level in this diagram is quite high. And the principle of mine water geothermal is that you can abstract or pump out water that's relatively warm. It's not hot, it's just warm. It's maybe between 12 and 20 degrees centigrade. So you abstract that hot water and then you bring it into a heat pump. So this is an image of a very simplified heat pump. And a heat pump, it runs on electricity and it has something called a coefficient of performance of about 4. So you basically put in a quarter of the amount of energy you get out, the amount of heat you get out. So it's an efficient means of using energy. And then you have a separate loop which takes the warm water you've taken out through the heat pump in a different loop. So it's not mine water, it's a different water, and you can use that to heat homes. because you've boosted the temperature using your heat pump to say 50 or 60 degrees. And then what you do with mine water geothermal is you put your cooler water back into the mine system. And this is all, the mine water itself is all within a sealed system. And you're not removing vast quantities of water, and it's not huge temperature differences, but it's still a lot of volume of water that is within these old coal mines. So if this is such a good idea, one question is why hasn't it happened before? And I'm not really expecting you to read all the different things that are on this slide, but really what I wanted to stress is the reason technologies like this haven't happened before is it's complicated. There is no one single technical factor or economic factor or licensing. It's a real combination of factors. And I mean, ultimately, it does boil down to the business case and the economics. But what that means is there's a lot of both research work to do, innovation, new tools and so on work to do, and there's a lot of engineering and economic work to do to make things like mine water heating work. If we look at a map of the UK, on this map, the coal mining areas are in this kind of blue hatched colour, and the different coloured blobs are mine water heating schemes that have either existed and stopped working, that's ones in blue. Mine water heating schemes that are active, those are in red, ones that are being developed in the kind of yellow, and ones that are on the horizon in green. So there are mine water heating schemes across the UK. And the photo down here is a scheme that was running in Glasgow in Shettleston for many years and heated about 16 homes. So we know it's a technology that works, it's just not being widely utilised. So we have on the top bit of this slide, I've got some words, demonstrator and commercial schemes. So we know that some people are doing this, using this technology to get heat, to heat homes. They're doing it for commercial reasons, and it's working, but only in a few cases. But we also need to take this technology forward. We need subsurface observatories to do research in, and that will help us to measure things in the subsurface with a lot of detail through time. It gives us flexibility to do research that you couldn't do on a scheme that was actually heating people's homes. And it gives us lots and lots of environmental information about the impact of the technology. So on this slide, I'm sure some of you will recognise straight away the section that I'm showing at the top of the slide. Graham certainly does. But really, this section of coal-bearing strata at Spires it sort of exemplifies some of the things that we see in rocks, coal-bearing rocks, which are that they're very heterogeneous. There are lots of different types of rock, and we also see in this cliff face, we see quite a lot of small faulting within the cliff face. So doing anything in coal measures for energy is potentially quite complicated because the rocks are quite variable. And then we've added, as humans, we've added another layer of complexity to these rocks, because what we're looking at, obviously with mines from heating, is that miners have been down under the ground and they have mined out big voids in the ground. So this photograph is of a longwall mining face, and the photograph on the left-hand side is of steep and room workings that have been uncovered in an open cast site. And if you imagine these were underground and filled with water, you have big voids filled with water. And in the case of the longwall mining, you have the roof material collapses and you have very high permeability zones. So people have termed the flooded old coal mines under the ground an anthropogenic aquifer. So it's an aquifer full of water, which is at low temperature, but obviously increases as we go deeper, and it's that volume of water within the mines that is useful. If we pump it out, take some heat out of it and put it back in again, and then the water gets reheated. And we're setting up the observatory because there's a lot of geological research and geoengineering research that needs to be done to really understand these systems. So to look at what happens when we repeatedly take water in and out, to look at how much energy is in there, and if there are any impacts to the environment from doing those things. So just a final slide on kind of the background about why we're developing this observatory. So the observatory itself is a series of boreholes into the ground. It's a lot of monitoring of things like temperature, water levels, the chemistry of the water and so on. It enables people to get samples, and it enables, there's a lot of open data. It's one of the key principles of what the observatory is about, is that the data is open for everybody to use. So that's our kind of core capability. That's what's in the ground. And then what that enables us to do as geoscientists and geoengineers is to look at things like how big is the resource, the mine water heat resource, how long is it going to last? That's the resource sustainability. What risks are there in developing that resource? So lots of scientific questions come from having these boreholes and so on in the ground. And then what those scientific questions help us to answer is a range of kind of things which will actually make these kind of technologies happen more widely. So things like people being accepting of the technology because they can see it's worked somewhere and they can see there's not been problems. Changes in government policy to make it happen more easily, changes in licensing, and methods to make it more economically viable. So that's really the rationale for why the UK government has funded this underground observatory in Glasgow. It's to try and do the science to enable these different technologies to happen and to understand any impacts that they might have on the environment. Okay, so I'm now going to actually talk a bit more about the actual observatory in Glasgow. So I'm just going to start with an overview of what the observatory kind of actually is, what the kind of physical presence of it is. So I'm going to start up on the left-hand corner. So the thing which has kind of cost the most money, I suppose, and taken the most time are some boreholes into the ground. So drilling those boreholes, an example of some of the core from the borehole up here, and creating research compounds, such as you see in this photograph. And the boreholes themselves have got a lot of sensors down the hole, so they do a lot of measurement of temperature, of electrical properties, and so on down the boreholes. So they're very sort of modern technology down the boreholes. And also they're being used for sampling and monitoring quite a lot. This is one of my colleagues sampling water from the boreholes. The observatory, we did quite a lot of stakeholder engagement, which means talking to people that are interested and talking to local people about what we were doing. And that's really important as we move to different sorts of energy, because as I'm sure a lot of you are aware, some energy technologies are less popular with the public than others. So it's really important to talk to the public when you're trying to develop one of these schemes. We've done a lot of what we're calling the environmental baseline. So that's work on the water environment, the chemistry and the gas environment, and also seismic monitoring. And that is there before we started doing any work at the observatory. And that's to record what's happening in the natural environment anyway. There's environmental change happening anyway. And so we record that before we start, and then we record it as we do research at the observatory so that we can tell if there are environmental impacts happening. So yeah, we've been doing a lot of environmental monitoring. And I mentioned before about open data. So there's a lot of open data on the website that anybody can download and look at if they're interested. And some of that is data that you download, and some of it in the future more so will be time series data. So for example, water levels or temperatures that are streamed live, or we download them and then they're uploaded to the website. So they're there for lots of different people to use. So that's kind of a fundamental principle of the observatory. So how did we drill the observatories? How did we make them? So on the right-hand side of this slide is a picture of one of the drilling rigs that we used to drill the boreholes. So we drilled the boreholes back in 2019. So it's a fairly average site investigation type drilling rig. And there's a picture here of us installing the casing into the borehole. And this casing had special sensor fibre optic cables and so on going down it. We've also tried to carry on the public engagement. So there have been various articles such as this one. So the journalist thought it was a great pun. Talk about the research being boring because we'd been drilling boreholes. So I'm not sure that was the best advert for our work, but it certainly raised the profile of what we were trying to do in Glasgow. So just about where we are up to with kind of constructing the observatory. So we started drilling a borehole in 2018 in a different bit of Glasgow. So I'll show a map in a moment. And we drilled in 2019 all the mine water boreholes and some environmental baseline boreholes. We've started doing the environmental baseline monitoring. We've tested the boreholes, we've hydrogeologically tested them, and I'll talk about that in a little while. We then started to get our monitoring equipment on site, and then COVID hit. And so we've been a bit delayed by not being able to travel and get things on site. But we're making good progress with what we call our phase 1 works in terms of creating this underground observatory. And then later this year, we are planning to put in some pipes and some pumps and some other headworks and a heat centre, small heat centre, so we can do pumping at the observatory, like in the diagram I showed before, where we can pump out hot water, take some heat out of it and return it to the mines for the purposes of research. So it's quite a small setup, but it's at scale, so it enables people to come and do research like it was a real scheme. And it will enable subsurface change to happen and for people to be able to monitor that. Okay, so this next image is an aerial photograph of where the observatory is. So I'll just spend a bit of time explaining whereabouts the observatory is. So we're looking towards the city centre of Glasgow. So we're looking sort of towards the west. Clearly this is the River Clyde running through Glasgow. And most of the observatory is in a place called Culinary, which is on this big meander of the River Clyde. And at the Culinary site, we've got 11 boreholes. The ones in purple are environmental baseline boreholes. So they're there to monitor what's happening in the environment. And they tend to be shallower. So the deepest ones are about 40 to 45 meters. And then the green boreholes are the mine water boreholes. And they're at about 50, they go down to about 50 meters and about 90 meters. And they're in pairs. And they're in this triangle shape to help us understand the flow direction of the groundwater. And clearly underneath this area are a lot of old coal mines, or we wouldn't have put the boreholes there. Also, we have our seismic monitoring borehole is some distance away because this borehole went to 199 meters and is our chord reference section. So this goes through unmined ground, and we got a core from it that I'll show in a moment. and it now has a string of 5 seismometers in this borehole. So that adds to the National Seismic Monitoring Network. In general terms, you can see that this area of Glasgow is it's an urban area. This is part of the Commonwealth Games Village that was built in 2014. You can see there's industry and there's housing, and it's an area of urban regeneration. And it was important that for an underground observatory, the location was typical of other parts of the UK or Europe where we have old coal fields. So the conditions on the Cunningar Loop, for example, the shallow subsurface on the Cunningar Loop was used as a site where there was building rubble, demolition rubble, all sorts of things in the shallow subsurface, and obviously there's mines underneath, but that's typical of many of the industrial areas of the UK. And so those are the kind of challenges we've got to use the subsurface. So what I'm going to do now is I'm going to talk to you just a little bit about the mines and drilling into the mines and so on, and the boreholes. So just while I've got this photograph up, the mines that I'm going to talk about came from a colliery called the Farm Colliery, which was based in this area where I'm moving my cursor around. So the colliery was down here, and then there were roadways and workings coming out all the way under the Cunningar Loop and under the Clyde as well. So yeah, the Farm Colliery is in South Lanarkshire, and it was active from about 1805 to 1932. And there's a really good description of much of the Farm Colliery in a book that was published in 2020 by Colin Finlay, Bob MacDonald and Joe Cunningham, looking at the coal mining history in Rutherglen and Cambuslang. And the picture on the front of their book is actually at Farm Colliery, and this is a Newcomen steam engine, which is now apparently in the Industrial Heritage Museum at Cape Bridge. It was one of the preserved steam engines. So we have a good understanding of the colliery that the coal mines that we're targeting came from, which is kind of nice to understand that. And in geological terms, we're penetrating the Scottish Middle and Lower Coal measures. And there were 5 coal seams that were extensively mined in this area, and 7 altogether. And on this stratigraphical section on the right-hand side, you can see the thick black lines of the coals. And I've put some stars down the side. So the 3 topmost thick coals are the Glasgow Upper, the Glasgow L, and the Glasgow Main. They're the ones we penetrated within the boreholes for the observatory. And then there are other mined coals which have got the blue stars next to them, including the Glasgow Splint Virgin and the Kiltung, which is in the lower coal measures, is just off this section. So there's a whole sequence of mined coals coming out from the Farm Colliery in this area. And the boreholes that we drilled, this is a geological cross-section with the made ground and the superficial deposits, and you can see just a representation of the boreholes going down into the coal seams in this area. And this slide shows the actual results of drilling the boreholes into the coal mines. So it's 4 of the boreholes, and you can see that some of them went into this top coal mine working where there were stoop and room workings and waste. And then the deeper boreholes go into the Glasgow Main, which in both of these cases was a void, a water-filled void. These boreholes, we have the cables going down the boreholes that are fibre optic cables and resistivity tomography cables, so we can do cross-borehole imaging. And the boreholes are targeted, they're screened at the mine working intervals, and they're cased the rest of the way down, so that any water that we're looking at is from the coal mining interval. And then they've got data loggers, hydrogeological data loggers down the boreholes. So the next slide is to look at the deeper borehole, just to give you some nice pictures of some core and some fossils. So this was the only borehole that was cored, and you can see that as in many carboniferous sections, we've got some nice plant fossils and some marine bands, good section of what's called locally the Cambuslang marble, which is a really fossiliferous horizon. And this core has been taken to BGS in Keyworth, where there's a new scanning facility for core. So they've taken very high resolution pictures of it and done CT tomography and geophysical and geochemical scans of that core. And obviously we've done logging of that core. So I was just going to have a few slides about drilling into mines, because it was really nerve-wracking, I suppose, drilling into the mine workings, not knowing exactly what you were going to hit when you drilled into the mine workings. So this slide is to illustrate a little bit about the uncertainty of drilling into mine workings. So this picture at the bottom is a cartoon of what mine workings can be like under the ground. So there might be old-fashioned stoop and ream workings, so that's coal pillars and voids that are water-filled. There might be coal mining waste, or there might be open voids. And it's very difficult to predict exactly which of those it'll be when you drill your borehole. And in the picture up on the top right-hand corner is a picture of a geologist in an open cast site, I think in East Lothian. And these are old stoop and ream workings. Here's the coal coming along here, and here are the workings. And you can see just from this photograph that if we drilled two boreholes that are even a few meters apart, one of them potentially would go through the coal seam, the other one would hit the working, which if it was buried more deeply and was water filled would be a target for mine water heat. So there's a lot of uncertainty in drilling boreholes into old mines. This next slide is a map view of the mining information that we had before we drilled the boreholes. So you can sort of see the River Clyde coming round, and then this sort of brown colour, the brown hatch colour, is where the Glasgow upper coal has been extracted from the mines, and where it's double hatched is where on the mine abandonment plan it's recorded as stoop and ream workings. And then you can see the dots, which are our boreholes that we've drilled. So our boreholes intentionally, sometimes they targeted areas of total extraction, and sometimes they targeted areas of stoop and ream workings. In the other coal seams that we targeted, those coal seams underwent generally total extraction on the mine plans. And we had good handle on the height of the depth of the mine workings, because the mine plans have spot heights on them. So that enabled us to do a good 3D geological model before we drilled into the workings. We also have quite a lot of legacy boreholes, so all boreholes from round about that penetrated both coal and waste and mining voids. So we had that information. For those of you that are technically minded and interested in borehole design, I'll just very briefly show this image, which is a sort of schematic of the borehole, really just to say the boreholes have 3 casing strings, and they have an inner UPVC casing, and they have cables down the side, and they have a target screened interval. So I'm just now going to show a few pictures of drilling into the mines, looking at these different sites. We've now made it onto Google Maps. This is the drilling compounds when we were busy drilling the borehole. So in the first set of boreholes that we drilled into a mining waste of the Glasgow upper coal. So this is a picture of the mining waste that we drilled into, and some of the water samples that we took. And one of the things that we learned when we were drilling these boreholes, and in particular this deeper borehole, we had problems with the borehole when we were in the final stages of constructing the borehole and grouting up the annulus. And we learned that we really needed to put an optical camera down the borehole and do some logs before we finished constructing the borehole. And as a consequence of that, the next slide that I've got are some nice pictures of an optical camera that went down the borehole and penetrated and visualized really the mine workings and the coal. So I'll just explain what I'm showing on these pictures. So on the left-hand side, this is going down the borehole, and this is an optical camera, and this is the Glasgow upper coal, which in this borehole was intact. So you can see a thick coal here. So the coal was intact. It was a coal pillar in the upper, and then carrying on down in the borehole, we went through a waste of the Glasgow L coal. So this is what it looks like. It possibly on your screens just looks kind of grey, but there are flecks of other colour, which is like a sort of packed breccia. And then finally in this borehole, our target was the Glasgow main mine working. What you can see here, this is the sandstone roof of the Glasgow main mine working. And then there's just a black hole because that's the water-filled void. And then we can see at the bottom of the mine working a disrupted floor. And there are various things that happen in old mines. Sometimes you get the floor lifting and you get disruption on the floor. So that's not unexpected. And on the other boreholes that we drilled, we saw similar things. So I think in this image here of the Glasgow L mine working, you can possibly see a bit better the kind of brecciated nature of the waste. And then again, we went down to this deeper mine working into a water-filled void. So what I'm going to attempt on the next slide is a video going down this borehole into this void. So hopefully this will work. If it doesn't, I'll just move on. Okay. I'm not sure the internet connection is really going to work, but might do. Okay. So this is going down the borehole to the Glasgow main mine working. At the moment, we're just going through dirty water, and in a minute we'll pop out. Okay, so I'm going to stop it there. So that was the end was the Glasgow main mine working is a water-filled void. Oh, I'm not doing very well here. Right, I'll move on to the next slide. So hopefully that gave you an impression of what it kind of looks like going down into the borehole, and just what it's like going into a mine working and the amount of water that's in there. So in the observatory, we've got a number of different boreholes, and they go into different types of mine working. And really the main point that was interesting was that there was more coal than we expected drilling the boreholes. We expected there to be kind of more mines, and there was actually a bit more coal than we expected left in place. So I'm just very briefly going to mention about the hydrogeological testing. So if you drilled an oil and gas well, your measure of success would be, have you hit oil or gas? In mine water heat, obviously you need to know you've got water and how much water you've got. So you can do standard hydrogeological pump testing. I'm not a hydrogeologist, so I'm not going to attempt to describe this in too much detail, but we got temperatures that were around 12 degrees C, and the chemistry of the mine water was relatively benign for mine water. And we got some very good yields of up to about 25 litres a second of pumping the mine water. So I'm just going to go onto this image, which is quite a complicated image, but I'll just try and explain it a little bit. So on this axis of a graph, we've got the water levels in all the different boreholes. So these curves are the water levels in the different boreholes. And then these blue bars are the rainfall in the area at the time. And then when we see a lot of different peaks and troughs within the water levels in the different boreholes, then that's where we've done these hydrogeological testing. And really what I want to stress with this diagram is that we had, we pumped on one of the mine workings that was high up, for example, and we saw responses in the mine working that was lower down. And we also saw a lot of response from the rainwater. And what this means for the observatory is that there's good responses to pumping in the boreholes, and we can see those responses in the other boreholes. So it's very good news from the science point of view. And we also know that we can get a lot of water out of it. Okay, so again, moving on fairly briefly, just to talk about the environmental baseline that we've got at the observatory. I mentioned before that we wanted to know about ongoing environmental change. So there's some pictures here of my colleagues who sample the soil for soil chemistry and the surface water. We've also been monitoring the groundwater chemistry, the groundwater levels, as you've just seen, and seismic monitoring, and the ground motion, whether the ground's going up or down. And on the next slide, I've just got an image to show the kind of surveys that we've been out doing of, this was a ground or soil gas survey where the fluxes of gases and within the soil were measured. And it's really important to do this kind of environmental baseline. So in the case of gas, it was important to know whether there was any mine gas coming out of the mines before we start doing anything at the site. You can see on this survey, it was before we started drilling any boreholes. And we found that we couldn't see any signals of mine gas coming out at the moment. And we've repeated these surveys a few times. So what that means is if we then start doing research at the site and there start to be signals of mine gas, we know that there has been an impact. So that's why it's really important to measure these kind of things before we start. So just to round off the talk then, I just want to talk a little about using the observatory, because all I've spoken about really is the work that the BGS has done in setting up the observatory and what we've learned. But what we really hope is that we'll get researchers from the UK and around the world come to use the observatory, and also people from commercial companies that want to test new tools. And this is a picture of our one of our research compounds. There's lots of empty plinths for equipment that we need to go and put on. But the boreholes are actually very shy. They're underneath these manhole covers, so you can't see them very often. But yeah, we very much hope that people will come and do lots of research at the site. And very simplistically, the kind of experiment that people could come and do is they could come and look at one of the boreholes, and they could pump water out of it, and then they can monitor what's happening in the borehole at a different depth, at a different coal seam, and in those boreholes that are about 100 meters away. And that will tell people how sustainable the mine water heat resource is, how the water's flowing between the different boreholes and in the mine workings, and does it matter what sort of mine working we drill into, all those kind of questions. And I mentioned before, there's a lot of open data out there. So one of the things that people might be interested in doing with open data is looking at big data and data analytics. Letting kind of computers live on a lot of the big data sets. And there's lots of other things that people might come and do. They might come and test sensors down the boreholes, look at how to stop bits of the equipment that we use for mine water heat clogging up and that sort of thing. So just to round off then, my final point is that in summary, there is a big potential for mine water heat, because if we look at the map that I've got on this slide, the purple area are the mining areas in central Scotland, and the grey areas are the urban areas. So there's a real coincidence of where people live with where the old coal mines are, not surprisingly. A lot of the places were built up around the coal mines. But what that means is there's a big opportunity there for this potentially low carbon source of heat from the old mine workings across large areas of the UK where there's a lot of the population. And we saw previously on the map that there are schemes starting to be developed, and there is also a large proposal led by Strathclyde University in at the moment to develop various mine water sites across central Scotland. So there is a big drive to look at this technology a bit more, and the geology and the hydrogeology is really important in being able to develop that resource. So hopefully this evening I've given you a bit of a flavour for our underground laboratory in Glasgow, which is open for people to come and look at taking heat out of the ground, or actually something I've not really talked about tonight, but also storing heat in the ground. And we've seen a bit what drilling into the mines looks like and why we're doing it. So I will just have a final slide, which is just a thank you to all the people that have worked with us on this project, all the various companies that we've worked with, and a very large team of my colleagues at EGS. Thank you.